Thank you so much. And thank you to the organizers, the volunteers, and the staff for such an excellent conference so far. I feel really lucky and blessed to work at the U of A with Professor LeBlanc. I love the people I work with and I enjoy my research, but I'm not going to bore you to death with that today. Instead, I want to describe a capstone project I completed in a U of A graduate course on pedagogy and course design. The result was an algebra design for an algebra-based first-year course titled Quantum Mechanics in U. In this talk, I want to motivate and outline the form of this course. I'll emphasize that what I share here is only a design. It's not been tested in a real classroom, although I hope it soon may be. My intent today is to further a conversation about how we can engage all stakeholders in future quantum developments. Now, as we've seen in the session so far, these quantum technologies have incredible potential. These technologies are based on the theory of quantum mechanics, that is, a set of principles and rules that describe the smallest bits of energy and matter in our universe. From really messy and muddled beginnings over 100 years ago, quantum physics has risen to become a cornerstone of modern science. Yet, despite being so foundational, many of the public are initially ignorant or relate negatively toward quantum physics. A 2017 public engagement study from the UK found that people are generally familiar with the word quantum, at least in the context of household objects and their branding, but they don't really know what it means. One participant said, without knowing much or anything about the topic, it's hard to have much of a feeling about it. Another barrier to public involvement in quantum technologies is the common perception that is too advanced for the average person. The notion that physics is hard is one of the reasons why only 20% of Alberta high school seniors will take physics, far less than other subjects. One participant in the UK study said, quantum physics is for clever people only, and it would take a quantum effort to learn about it. In other words, in the minds of the public, a lot of them have the idea that in quantum physics, your IQ must be this tall to ride, and they're not making the cut. Now, I feel like a lot of this stems from the way we experts talk and express the ideas of quantum physics with the general public. For largely historical reasons, the dialogue around quantum mechanics has been laden with, quote, the language of the extraordinary. Now, as quantum practitioners, there's a temptation to describe and explain our work using words such as bizarre, weird, or my favorite, spooky. Now, quantum certainly has some counterintuitive aspects, but they are anything but mystical. Instead, as Christopher Queen and authors say, even if quantum physics is counterintuitive, there's no reason for quantum technologies to be promoted as inscrutable or enigmatic. Transistors, after all, are based on quantum phenomena, and ordinary computers that are built out of them are not perceived as towers of mystery. By emphasizing the strangeness of quantum physics, we may actually be entrenching misperceptions and isolating the very people that we hope to engage. Instead, professionals should strive to elevate the so-called quantum literacy of the general public. This means that basic ideas from quantum physics should become part of our cultural understanding and experience and engagements. We should talk about quantum superposition the same way we talk about cellular DNA. But how do we do that? One participant from the UK study, going back to that, had the insightful comment, when it crosses into your job or health or something that affects you personally, then we'll have feelings about quantum technologies. This quote illustrates that quantum needs to be contextualized in the lives of the people. To overcome misperceptions and understanding gaps, we need to concretely connect it to everyday experience. What's amazing is that we're at a watershed moment of quantum education. There's never been so many ways to talk about, relate to, or experience quantum physics. Organizations have responded with numerous educational initiatives in the form of courses, workshops, resources, and even games. There's also programs for STEM-inclined high school students to get involved. These initiatives are targeted and focused on training a future quantum workforce for the industries that are upcoming. They're trying to address the so-called quantum bottleneck, the workforce shortages that people predict will occur. Now, these programs are heroic and they're making a real difference for individuals. But these programs are actually significantly limited in the scope of the people that they address. A recent study from British Columbia, published last year, identified that only 13% of high school graduates will enroll in a STEM bachelor's program. Less than half of those will actually graduate with a STEM bachelor's degree. So by targeting quantum initiatives at less than 10% of the population, the vast majority of society remains quantum illiterate. These programs are also limited by their content. Now, most generally present the concepts and tools of quantum technologies in the framework of information theory. Now, this approach has some advantages that it requires only modest mathematical skills, which is really good for most STEM students. However, there's two issues in applying this to broader society. The first is that information theory is quite abstract for the average person. We don't directly manipulate bit strings and logic gates in everyday life. The second reason is that it risks being overly reductive. It may imply to learners that the only way humans can engage with quantum physics is via information. Now, information certainly has benefits, but I wish to show that quantum physics applies more broadly than this. So given that students can take broad first-year survey courses on biology, psychology, and economics, I wondered if a course on quantum physics could have a similar audience and scope. For the course I designed, I chose the title Quantum Mechanics and You to emphasize the numerous ways that quantum physics intersects our lives by the day, by the hour, and even by the minute. In designing this course, I wanted to make it as inclusive and accessible to students from all over campus. That meant we could keep probability and algebra skills, but advanced math was for sure definitely out. I also wanted to make it relevant and connected to the lives of the students, all without drifting into the language of the extraordinary and the bizarre. My approach is really in the spirit of Professor Chad Orzel's excellent book titled Breakfast with Einstein, The Exotic Physics of Everyday Objects. That is, exploring the principles of quantum mechanics in the context of everyday objects and experiences. In that vein, I want to share 4 examples of quantum technologies that you and I interact with regularly. Example number 1, GPS. Now, inside an atom are discrete energy states. If you address 2 of these states with light, you can construct a very precise and stable clock. Over 1,000 of these atomic clocks are flying above our heads inside orbiting GPS satellites. Now, a GPS clock has to be very stable. If it lost even a microsecond, it couldn't tell the location of this conference hall from somewhere across the river. Example number 2, solar panels. Now, as you bring atoms of silicon together and arrange them in a regular crystal, some of the electrons become shared among all the atoms in a quantum wave-like superposition. Now this wave superposition will reflect off the crystal and partially cancel itself out, leaving forbidden gaps of energies. These band gaps are what makes silicon so efficient at absorbing sunlight and makes it a really useful renewable energy source. Example number 3, MRI machines. Now, in the 2019-20 fiscal year, 2.3 million MRI scans were performed in Canada. One of those was of my wife's brain following an unexpected seizure. At the heart of an MRI machine are massive superconducting electromagnets. Superconductivity is an example of quantum entanglement between pairs of electrons. Without this effect, the required very strong magnetic fields and the crystal clear images would be absolutely impossible to achieve. Example number 4, SARS-CoV-2. Now, early in the pandemic, images like this one helped researchers identify spike proteins that became targets for future vaccine treatments. This image was taken with an electron microscope, a device invented during the Great Depression. We've seen images from electron microscopes today. This device works on the quantum wave nature of matter, of electrons. Mark Solomons gave an excellent talk yesterday about how they've taken an electron microscope and open sourced it so that anyone can build it. As we've seen in these examples, quantum technologies are more ubiquitous than we think, and these examples would form a basis in the course. Now, in designing this course, I identified and crafted 8 intended learning outcomes. I'll highlight 4 that I think are most salient. By the end of this course, students will be able to examine and appraise scientific data, claims, and concepts for making wise decisions. In other words, how do we responsibly consume science? 2, students will be able to explain foundational quantum principles such as discreteness, superposition, etc., and then identify applications of these principles in a variety of modern and future technologies. And 4, students will be able to assess the social and ethical implications of upcoming quantum technologies. Now, this course is organized into modules around these different topics and principles and their applications. These are some of the applications that will be covered in this course, including discreteness of matter and energy, tunneling, randomness and measurement, superposition and waves, and decoherence, along with entanglement and future quantum developments in communication and computing. Finally, to examine the social, legal, and ethical issues that surround these developments. Now, a critical component of this course is called the UN-essay. It's a free-form project where students will select a topic from the course that interests them, research it, and then present their findings in a personally meaningful way. This cross-stitch of a human skull is an example of an UN-essay submission from an anthropology class. Now, this assignment is critical for helping students connect with, personally, the ideas and principles of quantum mechanics. So, in conclusion, why does this all matter? In this talk, I've tried to answer directly the question posed by this conference session. How are we integrating quantum technologies into everyday life? I've tried to answer this question in the broadest possible sense, and in the way that includes the largest number of people. As we've seen, Quantum is more than simply information. Quantum is energy. Quantum is medicine and public health. Quantum is navigation and light and a host of other everyday experiences. And it's not just branding. We need to talk about these wider views of quantum physics. I believe it has the power to engage and include more people than ever. As the public understanding and perceptions change, this will only have positive back action in other areas, such in the industries, for the workforce, for teachers. Now, in presenting my course design for quantum mechanics and you, I've presented it as, I don't believe it's the final solution. I presented it as part of the conversation regarding how we can engage more people in quantum developments. It's my hope that all will be able to appreciate, experience the world-changing quantum, everyday quantum technologies. Thank you.